Great, thanks. Thanks to the organizers for inviting me to participate in this great workshop. It's nice to see some old friends, and unfortunately, I don't get the opportunity to meet some of the people, many of the people I don't know in this workshop, but hopefully in the future we'll be able to do that. So I'll jump right into it. This project was part of the recent SFB that we got here in Göttingen, Mathematics of Experiment. And one of the projects I have in this is together with Helmut Grubmueller. And the problem that we have is it's single shot femtosecond X-ray imaging. So you have some molecule or protein of interest. You shoot that molecule with a laser pulse. It's a very high energy and it destroys the molecule. The molecule is kind of streaming down suspended in some liquid. And before the molecule explodes, you capture some image over here. Most of the image is noise, but some of the photons in that image are coming from scattering events from the molecule. And then from that, you get somewhere around 10 to the 8th to 10 to the 9th images like this that you see here in A. And from that, you want to figure out what was the three-dimensional Fourier amplitude of this scattering event, or lots of these scattering events. So you're trying to fill out this kind of this sphere. And then once you have the whole sphere of these Fourier amplitudes, then you do a phase retrieval to then reconstruct the image of the object and be the electron density of the object in what they call real space. So mathematically, we want to find this electron density, which is some mapping from R3 to the non-negative reals, and the measurements, however, these are random variables. They're just you blast the molecule at some orientation that you don't know, and then you just record an image. So that's how I denote this with the Y. Whoops, and the Xi is just some index that we're selecting out of the sphere, which would then describe the orientation of the molecule. And so in the deterministic tomography model would be this data, the Y's, would be somehow would correspond to the amplitude of the Fourier transform of the electron density at some orientation S, some rotation S, the magnitude squared of that. And these phi's are then just the amplitude measurement in the Fourier domain, and the rows are the actual object in the physical domain. And so, right, at the moment, I'm not, and I won't go into too much detail at all, actually, on the forward operator, but this is in the far field, at least at the moment. But we have an extra difficulty, is that the S, which was parameterizing the Fourier transform, or Fresnel transform in general, corresponding to a particular observation that we make, is unobservable. We don't know that correspondence. So we really have a stochastic model where we have some observation that just comes to us at random, and we have to figure out both the orientation parameter theta, as well as either figuring out the density profile or the amplitude profile phi, or the density rho. So I'm going to think of this as just a stochastic feasibility problem. I'm just looking for any any element row, any electron density that with a high probability could explain the observations that we've made. And so this, I think of these, the possibilities as just sets of density. So the C would be the set of electron densities such that there exists some orientation of that density for which I can match the observation here. Or I could formulate that in the image domain. Then this would be the C hat. C would be the set of amplitudes such that there exists a rotation of the sphere in the image domain that would match the observation. And then my problem is to find the electron density rho that maximizes the probability, the maximum over all possible electron densities, the probability that that density is in any given set C that I have constructed from the data. So this would be the formulation of the problem in the object domain or the physical domain, or we can formulate the problem in the image domain. And once we take a feasibility modeling approach to things, so these would be the sets corresponding to the data measurements, but I can also add sets that include a priori information, like that I know that if the electron density is a non-negative real valued object, then the amplitudes are going to have symmetries. And so I can easily add symmetry constraints into this feasibility model. And so with this sort of stochastic feasibility model, we're approaching this as random function iterations. So the first step in this research is to at least frame the issue of what exactly I'm computing here. And with random function iterations, you start with some random variable with a given distribution mu, and you generate then a sequence of random variables. And the TXC is just a random selection of a mapping indexed by the X's at iterate k, and you just apply that mapping to our current random variable xk. And I've started studying these random function iterations together with Anja Storm and Neil Hermann. Neil was a former PhD student of mine. And this approach has been applied to infinite dimensional operator equations by Dan Butnario and Flam in the mid-90s. Where I'm also wanting to apply this to the analysis of distributed optimization, randomized methods for large-scale optimization, and it's also central to Markov Chain Monte Carlo methods, as Professor Diaconis has written a lot about. So our application of this is we're looking at the electron densities as being our random variables, and the random operator that we're applying to our current estimate for the electron density is just a projection onto those data sets that I showed you on the previous slide. And these densities now, these are random variables with some distribution. At a distribution at iteration k, we'll have distribution mu k. Okay. So, but before I get going too much, I want to. I think it's worthwhile kind of setting out that I'm approaching this more from the optimization perspective. So in inverse problems, the modeling is you're using the laws of nature and the fundamental equations to get more information and possibly solve your problems. And then you ask questions about when and how fast does a regularized solution converge to the exact solution to a model in the limit of perfect information, and the notions of well-posedness in the sense of Hadamard existence and uniqueness and stability. But in optimization, we're more faced with the laws of man, and that leads to non-smoothness and inconsistency and all kinds of awful problems there. And in optimization, at least the part of optimization that where I live, I'm mostly interested in answering when and how fast a particular algorithm converges to the solution of a given optimization problem. I don't ask too many questions about the optimization problem that I'm faced with. And then also in optimization, well-posedness is really thought of in the sense of Rockefeller, where perturbations of the problem don't lead to topological changes in the solution set, either existence or stability of constraint qualifications, and so forth. And then the last point, in contrast, that we've seen a lot of talks where people have really been looking at the operators and trying to tease out more and more information from that. Back in 2007 or so, I was collaborating with a physicist from Northwestern University, Lloyd Marks, on the Veen2K software toolbox for solving density functional calculations. And my command there was that I was not allowed to touch the model. So I will not be questioning the optimization problem that I'm posed, that I'm given. But there's certainly, thinking back to the fine talk that Thorsten gave last night, issues of existence and uniqueness of the ideal model will come back and have implications on rates of convergence of my optimization model in the end. And I'll talk a little bit about that. So back to random function iterations. I'm imagining that I've got just any mapping, Ti, mapping this, we're on a finite dimensional Euclidean space here. And they're indexed by this I. That I could be an uncountable set, possibly. And here's again our random function iteration. And the Markov chain associated with this, you've got a sequence of random variables. And so this would be a Markov chain if the probability, the conditional probability of my next iterate being in some set A depends only on the previous iterate. It doesn't depend on all of the other previous iterates. And so I would then describe this with little p, describe the propagator of my current random variable xk, given this set A, describing sort of what this mapping T, where that sends me, which random variable that sends me to next. Okay, so the random function iteration as a Markov chain. So this is a time homogeneous Markov chain with transition kernel little p, and what that transition kernel describes again is given some given some random variable x. It tells you what the probability of the image of x under T is of being in a given set A, where this is in the set in the Borel sigma algebra. Okay, so the problem now, there's a Markov operator associated with this Markov chain, and the Markov operator is a mapping on the space of probability measures. And that take values in Rn. And so the Markov operator is defined by this integral, and I'm just integrating my propagator against the distribution mu. And my goal in stochastic fixed point theory, or stochastic fixed point problem, is to find an invariant measure, or an invariant measure for this Markov operator P. So that would just be the measure, such that when I operate on this measure with my Markov operator, I get the same distribution back. Okay, so that's just a fixed point problem, but in measure spaces. And that's another big, conceptual thing here, is that my basic thing that I'm computing on the computer is I'm acting on this space Rn, this Euclidean space, and I'm generating points that I can view and look at, but those are just random variables. And behind those random variables are these distributions, and that distribution is really the state of my computer at that iteration. Okay, so just once more setting up all the symbols here. I'm working my basic space where the samplings come from. This is a Hilbert space, and I'm usually working on a compact subset of this Hilbert space. I is my index set of the random operators that I'm selecting in my Markov chain. The operators Ti, these are continuous. I'll put in stronger assumptions on them, but for the moment they're just continuous. The Markov operator, denoted by this script P, has a transition kernel little p. There can be lots of p's running throughout this talk. So this is the propagator. Again, it just gives the propagator of an electron density rho, say, for this set A is the probability of the image of that being in the set A. Okay, and I'll be using this that's a psi. This is a mapping from the probability measures on the subset G. It's a function, and it's given by this long, complicated expression. What this is, this psi on the inside here, psi sub t xi, that is what I call the transport discrepancy. And what that does is it measures the difference between residuals of my operator t at rho here and eta. And I'm just looking at the difference of those residuals here. It takes this simple form in a Hilbert space setting. You can do this in nonlinear settings, and it looks more complicated there. But then what this capital psi is then taking this sort of Euclidean transport discrepancy and formulating the same kind of object, but in the space of measures, because then I'm looking at the expectation over all of these possible, over the index set, basically, xi. Xi is coming from this index set I, and I'm looking at the infimum over all optimal couplings between, these are measures now, mu and pi. Pi is a specific measure it can only come from the set of invariant measures of the Markov operator script p, and then so I'm computing this expectation, taking the square root of that, and that's what I'm going to call, that would be my transport discrepancy in the space of measures. And this is what I'm going to use to describe the regularity that I need of the Markov operator to conclude things like convergence and rates. Okay, so again, here's our application to single-shot X-ray tomography. I got my operator T in the previous slides is now just a projection onto those sets, and I'm assuming that I can compute this projection easily, which I can. And so I'm going to start with some initial distribution for my electron density. This is going to come from, this is this script PG. This is the space of probability densities that are finite in the 2 Wasserstein metric on the domain G. And so my distribution at iteration K, is I apply my Markov operator K times to my initial distribution U naught. That's the law of the random variable rho K. And this will be measured in the Wasserstein distance. This D script sub W2 is given by this expression. This is just this here is the P Wasserstein metric, and I'll be working with the 2 Wasserstein metric. And the C here, not to be confused with the C sets of my measurements, this is the set of optimal or of couplings anyway between these 2 measures. So the main results that we have so far in this framework of thinking about this problem. So in general, suppose we have a firmly non-expansive mapping. I'll explain in a second in this box below. Firmly non-expansive mapping on a Euclidean space, Rn to Rn. Alpha firmly non-expansive, some constant bounded strictly below 1 for all I. And we have to assume that the Markov operator possesses invariant measures. Sometimes you can prove that easily. Sometimes you need some pretty deep theory to prove that. So then, if you have these 2 assumptions satisfied, alpha firm non-expansiveness and non-empty and existence of invariant measures, then for any initial distribution in the space of probability measures on Rn, the distributions of the iterates generated by the random function iteration converge in the Pokarov-Levy metric to an invariant probability measure for the Markov operator. Pokarov-Levy metric is a type of weak metric in the space of measures. So what is alpha firm non-expansiveness? It's characterized by this inequality here. And this is where my transport discrepancy comes in. It keeps switching every time it's the transport discrepancy is used to characterize this alpha firm non-expansiveness. If you ignore this term involving the transport discrepancy, what you have is it's just Lipschitz continuity with constant 1, right? But then a little bit stronger than that. But this is, I want to point out, this is not contractivity. It's a weaker property than contractivity. And in convex analysis, this inequality is central. It's to the theory of monotone operators. So this pops up all the time. And examples of alpha firmly non-expansive mappings are projectors onto convex sets, prox mappings of convex functions, convex projection algorithms. Now, when T is just an entire algorithm as a fixed point operator, these also are alpha firmly non-expansive. Examples of a projection of a convex algorithm would be like the Douglas-Ratchford algorithm in the convex case. So this is a very central concept. The other main result that we've come up with so far is something about the rates of convergence. This result is just saying that you'll converge. And this one is about rates of convergence. So, and this is about rates of convergence in the space of measures. So here now our mappings are randomly selected. TXCs are alpha firmly non-expansive in expectation now. And what that means is that this is very similar to the alpha firm non-expansiveness inequality on the previous slide, but now it's just an expectation with respect to these operators. And so that's what will give us convergence, fine. But to get a rate, we need something called metric subregularity. And metric subregularity in this particular setting, it boils down to the measure transport discrepancy, transport discrepancy on the measures, this psi here, satisfies this inequality here. And this is called metric subregularity. It's central to fixed point theory and a lot of analysis of optimization algorithms. And I've shown recently that this is necessary for any quantitative convergence result. So it's unavoidable. You need this kind of inequality. And it just says that the distance of a particular measure to this set of invariant measures, because that's our destination here, is bounded by some constant times the transport discrepancy in measures evaluated at mu here. And so it's a characterization of the regularity of the fixed point operator, which is the Markov operator, at its invariant measures, which is our destination. That's where we want to go. So as long as these two assumptions are satisfied, then starting at any initial probability measure that's finite with respect to the 2 Wasserstein metric, then the sequence will converge R-linearly to some invariant measure, and that invariant measure will depend on the initialization. So that might not be a unique point. And so at this rate, where the rate C, rate constant, is given by the constant alpha in alpha firm non-expansiveness and kappa that's characterizing the metric subregularity. If the set of invariant measures consists of a single point, single distribution, then you get Q linear or geometric convergence. Okay, so I'm going to quickly run through some first examples. Maybe I'll skip the examples. The first thing was to show that this framework subsumes the analytic framework that you would use to analyze deterministic models. And these are all just deterministic optimization algorithms. I'll skip over this. So it just says that this is the right kind of framework, just more general than what we're used to. Another big application in machine learning and large-scale optimization is solving very simple problems like this, just minimizing the sum of lots and lots of functions. And these functions are usually, in a lot of models, very, very nice, strongly convex with some convexity constant, modulus convexity mu, Lipschitz continuous gradients. These are really, really nice functions. supposing that the expectation of this has a minimum at some point, then just steepest descents, random steepest descents. So you pick one of those functions, take the gradient, go in the descent direction with that for that gradient with a step size that's governed by the modulus of strong convexity and the Lipschitz constant of the gradient. Then this will be how you generate your random sequence, and we can conclude that there exists an invariant measure for all step sizes bounded above by 1 over L, and that the mappings, these random mappings, are all alpha firmly non-expansive in expectation. And you can compute what that averaging constant is. It depends on, again, the modulus of strong convexity and the Lipschitz constant L and your step length. And we also can show that the Markov operator satisfies also this alpha firm non-expansiveness in the space of measures. If in addition we have metric subregularity of the measure transport discrepancy, then you can quantify convergence of these methods. But I want to conclude with a very simple example that most third semester bachelor students would understand. And that is with just solving AX equals B. And here M is less than N. So I have more unknowns than I have equations. And I'm an optimizer, or I've been talking about feasibility models. So I would formulate this model not as solving AX equals B, but rather just finding some point in the intersection of the hyperplanes associated with this system of equations. And once you formulate it as a feasibility problem like this, the first algorithm that you could think of would be cyclic projections. You just start with the mth row of this system of equations, project onto that hyperplane, project onto the next hyperplane all the way up to the first row, project on that hyperplane, and then repeat. And there's a theory for this. You can show this very easily, that if A is full rank, then this cyclic projections operator mapping here converges either finitely or linearly to some point in the intersection of these from any starting point. In fact, it converges to the nearest point of your starting point to the intersection. And then you give the students an assignment, program this. It's easy enough to program. There's a closed formula for all of those projections. It's great. And you give them some random matrix A that's 50 by 60, for instance. They program this up and they get a result that looks like this. And I don't know if you can see this on your screens. You get really nice linear looking convergence here. That we're looking at the difference between the iterates on the y-axis. The x-axis is the iteration counter. And right at around 10 to the minus 16, it bottoms out, and then you just see noise, right? And the students ask you, what's that? The theorem said that it converged. You said, oh, well, right, that's numerical error. You can't get better than 10 to the minus 16 with double precision arithmetic. Well, the theorem didn't say anything about that, right? And if you do a histogram on the difference between successive iterates in this tail, so I just took the last 4,000 iterates and then did a histogram on that, you see this kind of thing. So actually these iterates it's looking like, some random variables with some sort of distribution indicated by this histogram. Okay, so you go back and in the next lecture you say, okay, cyclic projections with errors. What do you do with errors? The common approach is you just add some error. You imagine you've got your exact projectors. There's a closed formula. They put it into their computer. It's exact, I guess. But there's round off error, epsilon k. Then the theorem would say something like, if A is full rank, then the cyclic projections with vanishing errors converges. What does that mean? That means these errors have to be summable, which means you have to go from double precision to quadruple precision to 16 to this, whatever. You have to increase your precision of your computations infinitely in order to get convergence of this, which doesn't explain this, because nobody does that. But my point is, with all of this framework, you can still say we're converging here. And what we're converging to is what these points are random variables. They're selections, they're instances, events from a distribution that's characterized by this histogram. And we're converging linearly to this distribution. But the other point about this, and I'll finish up with this, is that you have to model this correctly, because otherwise you won't get that conclusion. If you model this as an exact projection onto these hyperplanes with additive noise. So this is how I'm modeling these things, and then my cyclic projection operator looks like this, with natural assumptions on the noise, isotropic and things like this. Actually, you can prove that there doesn't exist an invariant measure to the Markov chain. So that doesn't work. And the answer to this issue is you don't want to think of the projections as exact with additive random error, but rather as exact projections onto a randomly selected set. So according to that way of thinking about the problem, here's my random set. And I've got a bunch of these random sets are the Xi and zeta here are random variables with some sort of distribution with very natural assumptions on the distributions of these random variables. And so these are my random sets, and I'm computing each time an exact projection onto these randomly selected sets. So it's as if each of my hyperplanes is kind of wobbling a little bit, right? And then this operator, this operator, randomly selected operator, is exact, but I'm selecting it at random. The Markov operator, the Markov operator associated with this guy possesses a unique invariant measure. The transport discrepancy, the surrogate function, is linearly metrically subregular. You can prove that with constant kappa. And so then you can prove that the distributions converge to an invariant measure for the Markov operator Q linearly with this rate. So, and that would explain this. And so what your computer is by the end of, by iteration 8000, your computer, the state of your computer is the distribution. And when you query your computer, you're getting a random variable from that distribution. So the next step is to apply all this to the single shot femtosecond X-ray imaging. With that, I will stop. These are some of the publications associated with that work. Thanks.